So, like was mentioned, I am Javier Mancilla. I'm the CEO and co-founder of Falcondale. And today I'm going to talk about not only about some technical things or some cases in general or some exploration in a lab. This is real stuff. We're going to show a case industry level in the finance sector. But first of all, what we're doing? What is our purpose? Falcondale is in development now to be a quantum software as a service that can be used in the finance sector, especially for credit scoring, fraud detection, and these kind of cases. And particularly, our solutions are tailored for NISC. So we're pointing to use quantum hardware or eventually post-NISC, but providing today a competitive edge of advantage in simulators. But let's go directly to the case. So here we can see what we're doing. Remember that for credit scoring, for example, you use machine learning models to classify good or bad payers, defaulter or not defaulters. And usually these models, these machine learning models, are measured by a metric that is called AUC, which is area under the curve. And having 0.5 is just flipping a coin. It's not adding value. The decision of the model, the prediction that it offers is not good. But if we have 1, it's like perfection. And it's very difficult to reach that point. And here we see the curve of how Falcondale increased the performance in AUC when we add our secret sauce, when we add different methods to improve the quantum kernels that we're creating until we surpass a vanilla implementation of a quantum support vector classifier, a support vector machine, or even the state-of-the-art in credit scoring these days, which is gradient boosting or XGBoost. But let's go to the case that we're presenting today, which is with a company. It's Fintonic. Not sure if you are aware of this company. It's a Spanish fintech. It's a group, actually. It's a holding of Fintonic, WANA, and Open Insights. And what they do? They are a credit broker. So they engage with the users and give these leads or prospects of credit to banks like Santander or other financial institutions. And they are not new. They have more than 10 years in the market. They have 500,000 of users that they are connecting their accounts through open banking. This is really difficult to have. A lot of banks are trying to deal with open banking and extract information, which is very important to analyze and underwrite the users and provide a better scoring to actually the partners of Fintonic. And in this case, one of the partners is internal, is their own company, is WANA. But they have a very small funding, and they need to create a very specific and tailored and bespoke credit scoring system. Let's go for the challenge. The problem here of a lot of financial institutions, not only Fintonic, but also neobanks and banks, is the scarcity of data. It's really complex sometimes, especially for gradient boosting, to work with 500 data points, 2,000 data points, or even 5,000 data points. Gradient boosting are not performing always well, and other methods either. They are highly imbalanced. So when you need to predict default, sometimes you have 5% of your data set with default, or 3%, or 2%. The models, again, the classical models are dealing with problems there. And in this particular case, they have a problem with over-engineered features. Usually, we think that if we have more features, the model will perform better. So they create more than 300 features. But the problem is that this is adding potentially noise to the model, and it's not giving any advantage in this point. And they fight for a long time to have a better AUC. They are struggling to have better AUC, this performance that I shared previously. So what is the method that we're using? We're taking advantage of a higher dimensionality that quantum kernels can offer, and quantum in general, to specifically have this extra mile that we're looking for. How we can increase this AUC if they are fighting for so long to create a better performance in the model, and they are not reaching any particular advantage. So this is real data. This is really well designed, right? But it's real data. It's a real representation of data, but we use 1 qubit to show this in a block sphere. So this is a 2D representation of two classes, default and not default. And you can see that there looks like more linearly separable, right? But here, almost impossible. So we are trying to take advantage of this. And I'm going to share now what is the product that we're developing that puts together everything that we're doing in terms of algorithms and the process that we're following. So you can use public records in terms of financial institutions, of course, open banking, financial behavior, credit bureaus, or any alternative data to actually send this to our SQS, our systemic quantum score, and we're going to process and provide you a low effort score with higher accuracy. So let's go back to the case. We receive 300 features, more than 300 features. We use Quantum Inspire to reduce them to less than 30, and later, to use the limited amount of qubits that we can use these days, we go below 10 features to play, of course, with less than 10 qubits. And we apply this, which is our secret sauce. I know that potentially there's a lot of technical questions here, but we're going to release a paper next week that will be an archive, but also all our team, I'm not sure, team of core DBX and Falcondale, you can raise your hands. Thank you. Everyone can talk to them, and actually we can provide you the paper today if you want to look at it and take some notes or understand what we're doing. But basically, we develop an evolutionary algorithm that will adapt the model to each type of different data set. We test a lot of data sets, and sometimes with classical approaches or classical implementation of QSBC or anything like that, the model performed really differently. But now we have the chance to create a population with different Pauli-based chromosomes, let's say, or Pauli words. We create and combine everything to create feature maps, and later we optimize these future kernels with a maximization of eigenvalue and also a gradient descent. At the end, we select the best classifier, and what we have, I think you are really interested, I guess, in the results. So here are the results. You can see that we divided the data set in 3 levels: 10% of the data set, 50% of the data set, and 100%, right? The whole data set. And we can see that XGBoost, which is the gradient boosting, and support vector classifier are performing not that good, right? And let's add to this that this is not a classical XGBoost with the plain approach. This is a version of hyperparameter tuned of XGBoost. So it's the best performance that they can get with 10%. And SQS is having almost 17 percentage points better in AUC, surpassing, comparing this with XGBoost. And with 50%, the XGBoost is getting better. But SQS is maintaining the performance really high, above 70. And when we reach the whole data set, we are performing close to 0.75, around 0.73, and XGBoost is not reaching the same point that SQS. When we talk about a few points in AUC, we are not talking about something that doesn't mean anything. It's about reducing default. It's about saving money. It's about having more profit of your portfolio. And what happens if we do this exercise? We just use 10% of the data set to train the model and 90% in the prediction to test, right? We put XGBoost again, SBC, and SQS is performing better. So we demonstrate also that the model can generalize a lot better in this case. And remember, don't forget this, XGBoost and support vector classifier are using 360 data points, no, 360 features, and SQS is using less than 10 dimensions to perform this good, okay? These are the summary. So best SQS AUC with 10% of the data set, 0.82. Best SQS AUC using the whole data set, 0.73. And best original XGBoost best effort of Photonics team, in this case, particularly WANA, 0.70. What these 3 percentage points means? We are saving losses in a year of 1.1 million euros, in a very short funding portfolio that they have because they have only 12 million for the whole year. So they want to scale, but to scale, they need to be sure that they can secure a good default ratio. So a little bit more about Falcondale, what we are pointing out. Remember, we are not quantum inspired. We use some tools. We use some tools for feature selection, but our solution is tailored for NISC. We are looking for post-NISC machines or fault tolerant because we can easily switch what we are doing today in simulators and providing advantage to concrete and real quantum hardware in the future, so we can exponentially grow when the time comes. And also, we're working with Fermionic. I think some of the guys of Fermionics are here. So we're working with Fermionic to emulate the noise models of some machines in OQC, particularly Toshiko. So we want to keep developing these quantum kernel approaches to run in actual quantum hardware. We know that banks, neobanks, fintechs, financial institutions in general are very sensitive about data. So we are pursuing these certifications that we will have in a few weeks. And also, we are preparing our system to work with synthetic data, anonymized data, and so on and so forth. And this is our team. So very prime team in my viewpoint. I love these guys. And all of them have a lot of experience in quantum machine learning or management, but particularly quantum machine learning. And most of them have PhDs or they are PhD candidates. And last but not least, this Falcondale solution that is going to reach the market in a few months, and now we already have some clients in the line, is created by a joint venture between Stafford, which is my original company. They have some partners here of Stafford, that we provide consultancy services to financial institutions for more than 2 years. So we understand their problems. We understand what they need. And for the other hand, we have CordiVex, which have more than 10 years as a leader in software engineering in LATAM and also in data science. And now they are looking at deep tech. So stay quantum, and please reach us if you want more information. Thank you.
Thanks very much, Javier. It was very interesting. So I just want to remind everyone, if you have questions, please use the link at Slido and send them in there. We do have a couple of questions. So one of them is, if you use less than 10 qubits, as I think you said, that you can simulate classically, how do you know that your approach will scale and be able to scale up to bigger data sets?
Yeah, we are, in this case, we prove, and we are really sure that the generalization capacity on lower and smaller data sets is looking good. But the, excuse me, the difficulty of a scale these days is, since we are testing with classical computation, compute a kernel of these sizes is really problematic, right? So I think a middle term will be working with HPCs or something more sophisticated, more powerful, let's say, to keep increasing the capacity of the data set. And now, of course, what we can point out is working with financial institutions that are launching products that have smaller data sets, or also companies that are serving credit to SMEs. Usually, they have a smaller data set than when they work with individuals. They have higher data sets. So that's the approach so far, and we expect to scale in the future.
Perfect, thanks. And the second question is related to something that I was wondering as well. So financial institutions and banks are kind of nervous about adopting very state-of-the-art machine learning models and neural networks, for example, for all these problems. So can you achieve similar explainability as XGBoost, or explain what the algorithm is doing and make financial institutions more comfortable about adopting it?
Yes, this is actually true. So we know a lot of financial institutions that are, of course, regulated, and they need to have the explainability of how you decide this or not. So mainly you need to remember that we have quantum enhanced machine learning. So we're enhanced a classical method at the end. So an SBC is classical, but you produce an information that is more, I don't know, more representative that can be actually be divided and we can classify the users better. But what we're thinking is we can create a second layer. So they can decide, for example, with an XGBoost, a gradient boosting, as a second layer, they can use a quantum or to define affordability or use something extra that not strictly the decision. It's more like an enhancement of the decision or an extra that they can provide for the decision, but not the decision itself, until we match the regulations that are required for these cases.
Sure, more like a feature extractor rather than...
Exactly.
Perfect.
Share the feature importance and so on and so forth.
Yeah.
Yeah.
Cool.